In this video, we're going to do some practice problems of drawing structural isomers. So if I give you a general formula, can you draw a variety of structural isomers of that structural formula? So the main steps are listed here. What you do is you would first use the molecular formula, or general formula, to determine the type of molecule that the molecular formula represents. You would then start by just drawing an isomer that has the longest chain possible. And then after that, you make variations of that molecule by taking off some of the carbons from the parent chain and adding them, putting them as substituents. Or if there's functional groups, maybe move this functional group around, put it at a different carbon number, and that will lead to a different molecule or a structural isomer. What you can do after you've done all your chain and branched versions is you could try to make some rings if that's possible. And then just in your last step, make sure that you've actually named the molecules to see that they're different and not just the same one, just drawn from a different orientation. So let's see an example. It's always best to start off with some examples. We'll start with something simple, C4H10. We're going to draw all the structural isomers of C4H10. There's 4 carbons and 10 H's. And you'll notice that that falls under the formula of CnH2n plus 2. So we know this has to be an alkane. Doesn't matter what the alkane looks like, as long as it has 4 C's and 10 H's. So what I'm going to do is I'm going to start off by drawing the most simple one, which is the chain with just 4 carbons in it. So 1, 2, 3, 4. So we've drawn butane. And then I'm going to draw for my next one a 3-carbon chain, but I'm going to put one of the carbons and its hydrogens as a substituent. So I'll get 1, 2, 3 there, and then this here. So I have 2-methyl, and then propane. 2-methyl propane. And it looks like that's all I can draw for C4H10. If you take a look over here at this table, you'll notice butane only has 2 possible isomers. So I've drawn all of them. And I know they're structural isomers of each other because this is C4H10. And this is C4H10. And they have different names. So they have different bonding sequences where I basically just took this and put it here, roughly. And that gave me an isomer, a structural isomer. Okay. Next, we're going to try C5H12. So we're going to draw all the isomers of C5H12. Notice that C5H12 also follows the CnH2n plus 2. In other words, it's also an alkane. And I'll start off by doing just the regular plain parent chain with no substituents first. So 1, 2, 3, 4, 5. So we drew pentane. Next, I'll try to put a substituent somewhere. So I'll make a 4-carbon chain and then put a substituent here. And so I'll get 2-methyl butane. Just going to do this in a different color to show you. Some students might do this and might go, okay, great, I did that. Now I'll do this. And they'll say that's another structural isomer. Well, no, it's not. You'll notice it's also just 2-methyl butane. So that's not another structural isomer. It's the one you've already drawn, just from a different orientation with a different rotation going on there. So you wouldn't redraw that. Okay, so I can't move that one substituent anymore. Maybe I could try making a 3-carbon chain with 2 substituents on it. Let's try that out. I kind of go lower and lower every time. So like this and like this. So I got 1, 2, 3. And then on carbon number 2, I have 2-methyl. So I have 2,2-dimethyl propane. And these are all C5H12. Now, some students might have said this. They might have said, well, why don't you try drawing a 3-carbon chain, but then putting an ethyl on it? So like this. If you look at this carefully, Notice that this is not going to be something different. You've actually drawn this. You might think, oh, here's my parent chain, 3 carbons, and so I have 2 ethyl propane. That's not true. The parent chain is actually this. So 1, 2, 3, 4, right? Or you could even go 1, 2, 3, 4. It doesn't matter. But the whole point is that this would actually be just 2 methyl butane, just drawn from a different sort of orientation or view. So it's not an additional one. So just be careful. That's why I always say name those molecules that you draw, because it's so easy to be tricked. Like, oh yeah, that does look different compared to the other one I drew. So it must be a different molecule. No, it's just you rotated it and bonds moved around a bit, or rotated a bit, and you think it's different, but it's not. So let's go take a look at that chart there to see how many. So pentane can have 3 only, and we got 3. That's what we wrote down. So before we go do some more practice problems, take a look over here at this table. You'll notice that as the number of carbons goes up, this is for just alkanes here specifically, the number of isomers starts to go up as well, right? So by the time you get to 10 carbons with 22 H's, you have 75 possible isomers. So as you can see that as the number of carbons increases, the number of structural isomers also increases. And so you can provide the example of C10H22 having 75 isomers, but something like C4H10 only has 2 isomers. And it makes sense, right? Because the more carbons and hydrogens you have, the more different ways there are to connect them together. Like the more pairs of pants you have and shirts you have, the more different outfits you can kind of wear, mix and match. Similar idea. Okay, so next let's go try C4H8. So C4H8, it follows the formula CnH2n, which we know could be alkene, or it could be cycloalkane. So let's just start drawing our most simple alkene straight chain. So this is 2 carbons and 3. So 1, 2, 3, and then 4. So here we have a butene. When I have alkenes, I like to move the double bond around because that counts as being structural isomers, constitutional isomers. Because as you move the double bond, you technically move the H's from one carbon to another. So I could get this but-2-ene, but then I can't really do any more. Like if I did this would be butene again, just flipped. It'd be the same thing. So butene and but-2-ene, those are the longest carbon chain with double bond that I can draw. Next, I'm going to try to shorten the chain and put a substituent somewhere. Let's try that. So let's try doing, so double bond here. And then putting a substituent, let's say over here. So 1, 2, 3. So it looks like we can have 2 methyl propene. And then this can also be a cycloalkane with 4 carbons. So you can make a square, cyclobutane. And then the smallest ring structure you could actually have smaller. This is 4 carbons in a ring. Why not try a 3 carbon ring and then put a substituent, a methyl substituent on there. And so you have your 1 methyl cyclopropane. And I believe you can only have 5 structural isomers of C4H8. So our strategy here was to first of all figure out what type of molecules you can have, and based on the formula, it looks like you could have alkenes or cycloalkanes, you could have The alkenes, we drew the longest ones first. We then tried to shorten it and make a 3-carbon chain with a substituent. And then after that, we decided to make ring structures when we ran out of double bond chains. There's actually different types of isomers you can add with double bonds called diastereomers. We'll see that in more detail later on. But for now, we're really only doing kind of the different bonding arrangements, but same molecular formula. Okay, so you can try the next one out yourself if you'd like. So pause the video, then return to see if you can figure out if you're on the right track. You can do that for as many of these as you'd like. And then again, come back and see if you got at least 4 of these. So I wouldn't always ask you to draw all the structural isomers, especially as the molecules become bigger. But I could ask you, draw at least 3 or 4 of the structural isomers for a molecule with molecular formula C4H10-8. So this requires a little bit of thinking here. The C4H10-8, if you remember back, this is the CnH2n plus 2 and an O. And so that represents essentially alcohols, also represents ethers. So same idea here. I'm going to try drawing the longest chain with an O in there. So there's 1, 2, 3, 4 carbons, and then I'll put an OH here. And then this is where you can kind of get creative with things. So here we have butanol. But then I can grab the OH and put it on a different carbon. So 1, 2, 3, 4, put it on this carbon here, and I get butan 2-ol. So that's just one way of doing it. You could also make a shorter chain if you want. So you can make 3 carbons, put an OH there, and then put your methyl here. So you get 2-methyl, and then propanol. Or you could have done, for example, 3 carbons, an OH, and this, and you could have got 2-methyl propan 2-ol. So it's always the same strategy. Draw the longest chain first, like the most plain chain you can, and then start, moving that functional group around a little bit. Once you've moved it around all you can, then try to make a shorter chain and move substituents around, and then you can mix it up by moving the functional group around too. And right now we've already drawn 4 without even getting into the ether possibilities. Yeah, but we can do that as well. And so really any ether will work out as long as it's 4 carbons. So we can put 1, 2 carbons and connect an O here, and then put 1, 2 carbons there. So 1, 2, 3, 4 carbons with an O in the middle. Maybe you could do 1, 2, 3 carbons connected with an O there, put 1 carbon there. That's a possibility as well. So it looks like, so we have over here 1, 2, 3, 4. So we have ethoxy ethane. Here it looks like we have 1, 2, 3. So methoxy propane. And I believe that is all you can make in terms of the structural isomers of C4H10. And what I sometimes like to do is I like to just double check, so I can go just research it, just do a quick Google search to see if you found most of the structural isomers, and it'll tell you if you did or didn't, and if you didn't, you can go and try some more out. I found, let's see, 1, 2, 3, 4, 5, 6 of them, and I think there is one more you could do. I missed it. I didn't realize this, and this is something because it's not a very common one. But you could do. Let's see. We could have a propane molecule and connect the methoxy group there. Didn't think of that one there. 2-methoxy, and then propane. Because it's a bit weird to think of this, but remember, this is a substituent as well, right? And so you can put that in carbon number 2, and you have 2-methoxypropane. So that, I believe, covers all these structural isomers of C4H10O. They could be alcohols, or they could be ethers. So it really does help to go back and take a look at the general formulas of a variety of compounds we saw to do these type of problems. So C5H10O. So this is CnH2nO. And if you remember, this would actually be, you could think of this as being aldehydes, ketones, and also cyclic molecules, like cyclic maybe alcohols or maybe a cyclic ether. Let's try to draw one of each. We'll try to do a little bit of variety here. So we'll do an aldehyde with some with 5 carbons in there. So 5 double bond OH, and so this gives us H3, H2, H2, H2. So that's C5, H5, 6, 7, 8, 9, 10 with an O. So what we did here was we drew pentanal. Let's do a ketone. So 1, 2, 3, 4, 5. We'll put the double bond O here, and we have H3, H2, H2, H3. And so we drew pentan 2-one. And of course, you could move this around. You could put the O in on the third carbon there and call it pentan 3-one. For the pentanal, you could take off a CH group and put it on as a substituent. My goal really is to get a diversity of molecules right now. So let's try a 5-carbon chain as a ring. So we'll get, and then we'll put an OH on it. We'll get H2, 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 and then H, and so that's 4, 5, 6, 7, 8, 9, 10. So that's 10 H's and an O. So we have a cyclic alcohol. So we have cyclopentanol. Let's try to do a cyclic ether, for example. We could do a 5-carbon chain with an O in there. So O, C, 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 and then, so that's 1, 2, 3, 4, 5. This would be H2, 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 H2. And so we have 1, 2, 3, 4, 5, 10 H's and 1 O. And so this is a cyclic ether molecule. We didn't really learn how to name these fully. That's not a big deal. Right now, you just drew a different type of molecule here. So you didn't have to draw this one if you didn't want to. You could have done another alcohol, cyclic alcohol, maybe another aldehyde, maybe another ketone. But the point is that you could draw at least 4 and recognize that there's a great diversity that can be variety that can be represented by this molecular formula, aldehyde, ketones, or cyclic alcohols and ethers. Okay, so let's try this one here. This is C4H8O2. So if you look at that, that's CnH2n, and then O2. So this looks like it could be a carboxylic acid. It looks like it could be also an ether, or an ester. Sorry, not an ether, an ester. Let's see if we can do that. So we can do a carboxylic acid with 4 carbons. So 1, 2, 3, 4. Double bond OH. We get H3, H2, H2. And so that's 4 plus 3, it's 7. Plus 1, 8. So we have a butanoic acid. We could do another one. We could do, for example, 1, 2, 3, double bond O here, OH, put a CH3 here. So we have H3, H, like that, and we have 6, 7, 8. So here we have a 2-methyl propanoic acid. We can try an ester if we want to. So C, double bond O, O. We need 4 carbons. So C, let's make this H2, H3, H3. And so that's 3 plus 2, that's 5 plus 3, that's 8. And then our 4 carbons and our 2 O's. So here we have an ethyl and then ethanoate. Ethanoate. We could do a 3-carbon carboxylic acid part and a 1-carbon alcohol part. So for example, we can get C, double bond O, O, then CH3, and then CH3 here, H2 like that. So this would be 3 plus 2, that's 5, plus 3, that's 8. So what we have here is a methyl propanoate. Propanoate. And so these are just 4 examples that I could draw for a molecule that has C4H8O2. And so if you recognize, oh, there's 2 O's in here, so the likelihood is this is probably a carboxylic acid or ester because I know what the functional group looks like, then it's just you're in a better position to actually figure out what you can potentially draw from here. Notice that every time I did name the molecules to make sure they were actually different and not the same. But really, to get good at this, you just have to practice and you have to get that experience. And so I would recommend just trying a bunch of these out, going through the strategies I mentioned. I put some video links here for other videos made by other people where you can look at their strategies as well, and just get practice doing this. And so as you get better at drawing isomers, you're also practicing your naming as well and your drawing at the same time. So all the skills come together for a lesson like this. It is a bit lengthy, but eventually you get really good at it. You get really quick and you start to spot trends and patterns and pick up on your own tricks that work better for you. So in this video, we saw how to draw structural isomers or constitutional isomers for a variety of different formulas. Get the practice in this note here, but also in other worksheets. And in the next video, we're going to take a look at the other types of isomers called stereoisomers.